Hello, how are we doing? This is Mike here, and in this video we're actually going to get to the calculus of parametric curves. So first of all, as we defined earlier, our parametric curve is defined as two independent relationships, both which are related, and in this example is a relationship of t, which is our independent variable. And these are our parametric equations. These are our parametric equations. And together they help us graph our parametric curve. And remember, this parametric curve has a direction. This has a direction, as we discussed earlier. That is the major difference between a parametric curve and a regular curve, is that a parametric curve has a direction. So, as just with any curve, we can calculate tangent lines to parametric curves. And that actually works out really well. So we just have to make some assumptions here. And our first assumption is f of t and g of t. G of t have continuous first derivatives, have continuous first derivatives with respect to t. Otherwise, this really wouldn't work. So we have to just make that assumption. In this class, we will. Calculus 2, we will assume that they will have continuous first derivatives with respect to t. And then we will also have to make the assumption, well, that's really all the assumptions we have to make. Well, I guess we have to say y is differentiable function of x. Well, I don't know if that's necessary, but let's just say that it's nice for us to know that y is differentiable function of x. He teaches me for not making notes prior to my videos. Bad instructor. So those are, well, this is really the only essential. This is really the only essential, but this one's nice to have. So this one's nice to have, not nice, nice to have. So there's a nice formula for us to determine the derivative of the parametric curve, and that's going to be dy dt is the derivative of y with respect to time over the derivative of x with respect to time. And this formula right here allows us a very unique opportunity, and it allows us to derive, well, more this formula. This formula here allows us to derive the derivative from the parametric equations without eliminating the parameters. So here we do not need to eliminate the parameter. We don't have to eliminate the parameter. So let's just go and look at an example. Let's look at a very nice example, one that works out relatively nicely. Let's think that we have x equals to cosine of t and y equals to sine of t, and this is bound between 0 and 2 pi, as we noticed earlier before. And let's say we want to find the slope of the tangent line when t equals to pi over 6. So let's just remind ourselves this is a circle with radius 1. And pi over 6 is approximately 30 degrees, so it's about right here. So the slope of this tangent line is going to be something that looks like this. So hopefully we all recognize that our slope here is what we are trying to determine. It's a negatively sloping curve, so we better get our derivative at pi over 6 to be equal to be a negative value. So let's go ahead and calculate and just show how easy this is. So if we want to find dy dx, we're going to take the derivative of y with respect to t and divide it by the derivative of x with respect to t. The derivative of y with respect to t is going to be, derivative of sine is going to be cosine of t over the derivative of x with respect to t is going to be negative sine of t. So our equation of the tangent line, still in the parameter form with independent variable t, is going to be negative cotangent of t. So if we want to find dy dx when t equals to pi over 6, all we're going to do is plug this in. Oops. And we get negative square root of 3 over 1. So we recognize here that our slope is equal to negative square root of 3. So hopefully that doesn't seem that complicated. It's just taking two independent derivatives and making sure that we are deriving them correctly. So take the derivative of y with respect to t divided by the derivative of x with respect to t, and that's going to be the derivative of our curve at any given point. So so that worked out a little bit nicer than if I have let this be in my functional form, because in my functional form I would have had two places here. That's not very exact drawing, but I would have had a plus or minus square root of 3. But in my parametric form, t equals to pi over 6 only occurs once, so I'm guaranteed to get the correct slope. So that's why this parametric form is much more helpful when it comes to working with non-functions or curves that are not as easily described in functional form. So there's an interesting part about what happens. So if we look at dy dx again in terms of the parameter derivative, I like to look at what happens in several circumstances. So when dy over dt equals to 0, but dx over dt does not equal to 0, here we'll have the second option, dx over dt, the denominator of the derivative equals to 0, but the numerator of the derivative does not equal to 0. And then last, when both the derivative numerator and the derivative denominator equal to 0. So these are going to be three cases that we're going to have when it comes to finding derivatives of tangent lines. So in the first circumstance, so let's think about this. So when we have dy dt equaling to 0, we know dy dx is going to equal to 0 over some number where the denominator is not equal to 0. So when our slope is equal to 0, we know that we're going to have a horizontal tangent. We're going to have a horizontal tangent. So in this circumstance, we're going to expect a max or a min. So over here, when our derivative is equal to some number divided by 0, here we have to assume that we're going to have a vertical tangent. We're going to have a vertical tangent. So that means that we're going to see a point where our curve is increasing vertically. So here's where we're going to have a vertical slope, or I'm sorry, an infinite slope. And then lastly, we're going to have a circumstance where we're going to have 0 over 0. And we're going to call this point something new that you've not learned yet. And we're going to call this a singular, let me rewrite this a little bit better, singular point. When the derivative has a value of 0 in the numerator and a value of 0 in the denominator. And at this point, we can really make no generalized statement that can describe the behavior of a parametric curve at a singular point. They must be analyzed, so each case is analyzed separately. So each case is analyzed separately. So we really can't say anything specific about singular points. However, if the numerator equals to 0, we're going to have a horizontal tangent line. If it's a vertical tangent line, we could have something that looks like this or looks like this. And at these singular points, we have no way for us to really what's going on here. So let's go ahead and let's look at an example. So let's look at an example, and we'll look at a non-singular point example. So I think that might help us a little bit easier than looking at something that is singular. So let's go ahead and let's say that we have a trajectory. of a plane, and it follows the parameters x equals to t, I think we said minus sine of t, and then we had y equals to 4 minus 3 cosine of t, and we'll just restrict the value of t to be greater than or equal to 0. So we'll say it crashes. It crashes at t equals to 10. So it's just a way for us to put this restriction into our problem. So it starts taking off, of course, at time equals 0, it can't be negative, and then it crashes at t equals to 10 seconds. So let's say we had some questions here, and let's say at what times was the plane flying horizontally, meaning it's not increasing or decreasing vertically. And then I'm sure you can guess what the next question one's going to say. It's going to say at what times was it flying vertically? At what times was the plane flying horizontally? And then what time was it flying vertically? So if we think about the relationship of dy over dx being equal to dy over dt divided by dx over dt, we know that it's going to be flying horizontal when the numerator of our derivative is equal to 0. So we know here that dy dt will have to be set equal to 0. And the same idea goes for, for a very patriotic value there, I don't know how that happened, that if it's flying vertically when the denominator is equal to 0, but we have to make sure that these 2 points simultaneously do not equal to 0. So hopefully that's nothing that's too bad. So this was the first example that we did in our series of videos. So it looks something like this, and this is just a basic depiction of what it looked like. So t equals to 0, so it came off, looked like this, did a loop-de-loop, came back, and maybe it just exploded, or I don't, that's bad news. It maybe just hit something, it crashed. So it stopped right there. So right now, if I'm seeing some horizontal examples, I'm thinking it's going to be horizontal right about here. It may be horizontal about there, and then maybe horizontal about here. So that's where I'm thinking it's going to be horizontal. It could be horizontal here, but I don't know. Something's probably going to happen at these endpoints, but let's investigate those. So let's go ahead and figure out where this guy has a horizontal, or where he's flying horizontally. So again, we're going to let dy dt equal to 0, and dx dt cannot equal to 0. So dy dt is going to be the derivative of our y parameter, so the derivative of this guy. So dy over dt is going to be equal to, derivative of 4 is going to be 0, derivative of negative 3 cosine of t is going to be 3 sine of t, because derivative of cosine is going to be negative sine, and negative 3 times negative gives us a value that is positive. So, so we have some very interesting circumstances that this will equal to 0 in a couple different circumstances. So, so I think, yeah, this actually makes it easy. Divide both sides by 3. So then we're just looking for where sine of t equals to 0, and this is going to be between 0 and 10 seconds. Oops, between 0 and 10 seconds. Running out of room there. So so this will equal to 0 clearly when t equals to 0, and then when t equals to pi, and then when t equals to 2 pi, and we have to go one more time because we're going all the way to 10, and t equals to 3 pi. So, so that's going to be when the derivative's numerator equals to 0. So then dx dt, and I like to do this separately, dx dt, and I do it right down here, is going to be equal to, take the derivative of x, so we're going to have 1 minus 3 cosine of t. So 1 minus 3 cosine of t, and we have to set this guy equal to 0. So in other words, we're going to subtract 1 on both sides, divide by negative 3, so it's going to be where cosine of t equals to 1/3, cosine of t equals to 1/3, which implies that we're going to have 3 circumstances of t equals to cosine inverse of 1/3. And then we're going to add and subtract that value to 2 pi. So we're going to have another circumstance where t equals 2 pi plus cosine inverse of 1/3. And then we're going to have our last point at 2 pi minus cosine inverse of 1/3. So that's going to be our 3 solutions to when our denominator equals to 0. And clearly, none of these values are equal. None of these values are equal. They will all be different. So we never have to worry about a singular point because there's never a value of t that will give us the same. We're never going to have the same value that will give us 0. So that works out really, really well. I'm really happy with that. And that was specific to this question. So here we're going to have these 4 points when this will exist. So hopefully that works out pretty well for us and we can see it. If we want to figure out when this is, all we do is plug back in. We can use our calculator. I'm going to do this by hand. So at this point, we're going to have t equaling to pi. So this is going to be approximately 3.14, which falls into our this is what falls into our parameter. This is t equal to 0. Yep, I feel pretty good about that. This will be 6.28, and this last one is going to be equal to 9.42, and these are all approximates. These are all approximate. So all of those values fall between 0 and 10. So at these 4 points, we're going to have the plane flying horizontally, and then plugging into our calculator. So just doing this now, cosine inverse of 1/3. So this will give me a value of t approximately equaling to 1.23, and then we're just going to add 6.28 to both of these and then subtract. So this will give us t oops, I don't know why I started there. Well, I could have just skipped that. So this will be t equals 7.51, then subtracting from 6 points. So this will be 5.05. So at those times, we're going to see the plane flying vertically, and that's going to be approximately here, approximately here, and approximately here. So that's how we can figure out where the plane's flying vertically and horizontally. In this example, we do not have any singular points, so that worked out very nicely.